Okay. Okay. Do you hear me like this? Okay, so I was saying my name is Andrea Ferretti. I'm from CNR Nano, and today I'm going to give an introduction to the GW method, covering from the basic theory to the actual practice. That is what we are going to use this afternoon in the and so on. This lecture is going to be followed by an introduction by Andrea Marini on the Yambo code. That is the tool we're going to use this afternoon. And here is the outline of the talk. So we are staying, today is the excitation day, so we have heard from Ralph about excitations that can be computed at the time-dependent DFT level. Here instead we focus on a different tool, both a methodological tool, a different theory, that is the GW theory. And so I'll take, as an excuse actually, to discuss this theory, I'll start from a problem that is how to compute and compare with the photoemission data. So I'll briefly describe what you can get out of a photoemission experiment, and then how this connects to the theory of Green's function. I'll give a bit of insight about what physical information can be obtained from the Green's function as a mathematical object, and then we look at approximations, how to compute a Green's function, approximations for the calculation of a Green's function, that is the GW self-energy, and then practical implementation, and eventually what you really have to bear in mind when running your own GW calculation. So what are the things you need to be careful about, parameters to converge, and so on and so forth. So somehow the most important bit of the presentation for the sake of today's afternoon is going to be this very last point. So let me get started with the looking at the ARPES experiment. This slide has already been shown by Ralph this morning. In TDDFT, we've been focusing on neutral excitation, so where situations where the number of electrons doesn't change upon the excitation. Of course, this is not the only option possible, and in a photoemission experiment, instead we are really looking at cases where the number of electrons changes. In particular, we are in direct photoemission withdrawing one electron from the system, and in inverse photoemission that is totally parallel, we are adding one electron to the system. So experimentally, what happens in the ARPES or the photoemission experiment, basically we shine light on our sample. By doing that, we excite the system, and one electron is expelled from the system, and the measurement is actually looking at this electron that gets out of the system, measuring its kinetic energy, plus we can add the angular resolution that then connect to the electron momenta, spin resolution, and so on and so forth. But what is measured is actually the kinetic energy of the outgoing electrons, and by a very simple and naive picture, if this is the electronic structure of my sample, and I'm shining a photon with energy hν, basically in the kinetic energy map or in the kinetic energy measurement I'll get out at the sample, I'll see a structure like this. That's somehow really parallel what we know about the electronic structure of the system. So this is really a way to measure the electronic structure of a system. When we talk and say we talk about the electronic structure of a system, this is actually the very experiment that gives us insight about what are the physical quantities we are talking about. And when we combine energy resolution with the momentum angle resolution experimentally, or momentum or quasi-momentum from a theoretical point of view, when we combine these two quantities, we obtain also a very nice plot of dispersion of bands and so on, plus broadening that we are going to discuss in a second, that are connected to lifetimes and so on. So somehow, I think it is also important to stress that this kind of experimental technique got impressive advances recently. So they can really measure things that are pretty amazing these days. And just going back to the theory, we can think of starting from the Fermi golden rule. So we have an initial state, a final state. The final state is the one that bears the photoelectron, and somehow we can think of the final state, at least at first, as an excitation of the charged state with the n-1 electron. The excitation is labeled with S, plus the outgoing electron with the kinetic energy K. Actually, this picture is still not the complete one, since I mean, it's not granted that these two pieces of information can be factored. It's not granted that the two are not interacting or interfering among each other. So this is just to get some insight. The final state can actually be written in this form here, where we have here the n-1 excited, n-1 electron excited states, plus this creation of the photoelectron, plus all the interference and scattering effect that occur from taking the electron from the system to traveling inside the system and out of the system, since at a certain point the electron needs to reach the detector, so needs to get out of the system. And let's say, in order to simplify the process that is quite complicated, this three-step model has been proposed, where the process is split into the excitation, and then having your electron traveling through the your system, and then further interacting with other electrons, losing energy and so on, and then transmission through a surface into vacuum, eventually to the detector. This second, so here it's just a bit of jargon, but it's relevant to mention. There are some intrinsic losses that happen upon the excitation, like excitation of satellite structures, so something that basically goes beyond our mean field picture. There are extrinsic losses, so energy losses that happen when your electron really, after the excitation, travels towards the surface and gets out of the system, somehow in the dynamics that happens after the excitation, plus the transmission to the surface. Usually, and we would like to focus at best on the first step, and then perhaps add on corrections for these other two steps in a more effective and modelic way. So in order to break down the problem, if we want to just focus on the first step, neglect the extrinsic losses, what is done is we simply drop all the scattering that happens to this excited state plus the photoelectron, and after this is somehow physically justified when the energy of the photoelectron is high enough, and basically this decoupling of the photoelectron with the excitation of the system left behind can undergo the name of sudden approximation. So we are decoupling, we are killing the interference effect. And what is interesting from our point of view is that when we do this, we end up with an expression for the photoemission photoelectron current, that is this, where this quantity A is the so-called spectral density of the system. So let's look for a second here. So this quantity is just, okay, the IJ matrix element here, where this is any basis, but here we are basically summing with a Dirac delta contributions that are from the excited states at n-1 electrons. This is pretty much similar to a density of states, so we have some prefactors, some weights with Dirac deltas. And indeed, I'm going to show this in a second. This is the very exact definition for an interacting system of the density of states. And there's a parallel for the n+1 case, simply looking at photoemission, direct photoemission. We are withdrawing an electron from the system, so we are actually looking at n-1 electron systems. And still in this review, just to connect a bit to the theory we want to look at, in this review by Damascelli and co-authors, they immediately mention the fact that ARPES, of course, benefits from a theory able to calculate properly the electronic properties of a system, but also give feedback, and the development of the experimental ARPES technique is extremely useful to fine-tune the theory. So as far as ARPES is well resolved and keeps on improving its resolution, we also have a direct experiment to compare our theories with. And the main point is that a very useful and effective mathematical object to compute the quantities that are needed to compare with ARPES experiments is actually the Green's function that somehow embodies the knowledge of the spectral function that we have just seen being somehow carrying the information we need. So let's look at quickly the theory of the Green's function. The Green's function, from its textbook definition, is written like this. So we have this time-ordered product of creation and annihilation field operators averaged over the ground state, at least in its zero temperature definition. And what is relevant here is that we have an electron part where an electron is added to the system. Then we have a time delay between T2 and T1, and the electron is then we take basically an amplitude, so the electron is destroyed. But the important thing that is kind of hidden here is that the dynamics from T2 to T1 happens with the Hamiltonian that has n+1 system. And in parallel, when we look at the whole part, instead we kill an electron at T1, and then we evolve the system from T1 to T2, and then take the amplitude again. And here the dynamics instead happens with the Hamiltonian at n-1 systems. So basically, dynamics means that the information about excited states is embodied there. So here we are embodying the information about the n+1 excited states because of these dynamics here. And here we are embodying the information about the n-1 excited states. If you want, just to compare with what Ralph has told this morning, if we were looking for an excited neutral system, this T1 and T2 would be the same. And we would basically, in order to make the density operator somehow, and so we would be evolving these two at the same time with the Hamiltonian that would be at that point at n particles. Okay, so that is the formal textbook definition. This is another exact definition. The Green's function is can be basically written as the sum over poles. This Fs plays those are Dyson orbitals or amplitudes that are defined in this way, again as projections of an electron added to the ground state and projected on an excited state at either n-1 or n+1 system. And these energies here at the denominator are just total energy differences, again changing the number of electrons in the system. And what is pretty remarkable of this expression is that this is pretty much is identical actually to the expression for the Green's function in a non-interacting system, except that in a non-interacting case, these are the one-particle orbitals and these the one-particle energies. Here, instead, the definition is different, and importantly, these are not orthogonal among themselves. While in an n-electron non-interacting system we have n orbitals that are orthogonal, here we have infinitely many Dyson orbitals, and since they are, the sum of their amplitudes is the same, so it's the number of particles, basically this means that these are not normalized ones. So somehow the picture we have to bear in mind is that when we have an interacting system, instead of having n Dirac deltas normalized to 1, we have infinitely many Dirac deltas, all basically with fading amplitudes. And as I said, we are interested in looking at the spectral density, and the spectral density, spectral function, spectral density can be computed from the Green's function in this way. So the spectral function is actually the imaginary part of the Green's function and can be used to represent the Green's function through this Kramers-Kronig like expression. So somehow this is really the density of information for the Green's function. And okay, when we take x equal to x prime, we have the spectral density. Then this is really the basic density of states, local density of states that we read in textbook, but in a formal many-body sorry, in a formal many-body definition. So the Green's function comes also in order to be computed. Basically, the knowledge related to the interacting Green's function can be recast into the so-called electron-electron self-energy, and the Green's function can be shown to obey this equation that is the so-called Dyson equation. So somehow all the complexity is here in the self-energy. This is the formal solution, and one can also basically show, here there's a mathematical detail that is when we have discrete states, that the Dyson orbitals, so what those quantities that play the role of orbitals, single particle orbitals in an interacting system, obey this equation. So what happens basically is that instead of the simple potential that could be an external static local potential, we have the self-energy that is non-local and non-Hermitian, and also frequency dependent, where the frequency dependency basically translates into the fact that each orbital feels a different potential. So far everything is basically exact. And one could give also, there are several ways or several representations that can be given to the Green's function. The problem of inverting this operator can be cast also in as a frequency-dependent inversion, and I can put this in the form of a frequency-dependent diagonalization or eigenvalue problem, where the omega frequency is just a parameter. And in this picture, since the self-energy is non-Hermitian, basically I end up with the left and right eigenvectors, and the eigenvalues are not just meant to be real, and all depend on some frequency. So I end up with a different representation. So before we had, before we had these two quantities that are just the complex conjugate of each other and real energies at the denominator. Here we end up with right and left eigenvectors that are not in general the complex conjugate of each other, and these quantities are complex. And those are just two different representation of the same mathematical object. Actually, the math here gets quite complicated, and basically, in order to get some insight, one could just realize that the most relevant structures, the peaks related to this Green's function are those occurring when a condition like this occur, and basically then one could simplify this picture saying, okay, I'll just keep in my representation only the poles that are relevant. This is can be called a quasi-particle approximation. And what I wanted to point out here is that if we compare these two representations, basically this is the so-called Lehmann representation versus the quasi-particle. We can get some insight about what happens or what it means to have an interacting system. So in this picture here, we have a number of Dirac deltas with an amplitude that changes and then eventually vanishes off. In this other case here, we have instead a real pole that is far from the axis, so it has a real spread and in a real lifetime, we'll see. The two objects bear the same information, they simply describe it mathematically in a different way. This is somehow quite convenient in order to interpret what happens, since we have just one particle that instead of being represented with a Dirac delta is just spread out with a finite imaginary part of the pole that gives a finite lifetime. But actually the math behind this is quite complicated, but the two representations are somehow exact. So just let's look at what are the new features that can be inherited in the spectral function of an interacting system. Here is a Dirac delta spectral function of a non-interacting case. Then we take a model and we take the self-energy to be dynamical, but we take it diagonal on the basis of the non-interacting eigenvectors. So I can write the Green's function in this way, and then in order to take care of get rid of the frequency dependence here that complicates the picture, I'll take a Taylor expansion, first order, so I have the derivative of the self-energy with respect to the frequency. And if I do this, I end up with an interacting Green's function that has this form. And so what changes with respect to non-interacting cases that I have a z factor at the numerator instead of 1. And this factor is called the renormalization factor and goes along with the derivative of the self-energy with respect to the frequency. Plus, besides the position of the pole, oops, it's fading away. The position of the pole is just this shifted energy plus an imaginary, finite imaginary part that gives a broadening. So overall, what we get here when including interaction in the description of the system is a shift of the main peak that we can call the quasi-particle peak, plus a broadening, and plus a renormalization. The renormalization can be shown to be connected to the area of this under this peak here. And since the area is reduced, basically it means that the spectral weight has to go somewhere else. And the somewhere else are basically satellite replicas or other features. So what we gain basically, or what we get when introducing interaction into the system is that we get a shift, we get a broadening, and we get spectral weight displaced all over. And this is the spectral function, and so if we want to compare back with the photoemission case, this is basically what we could think about. So instead of having this non-interacting case, we have the interacting one with main quasi-particle peaks, satellite structures, and so on and so forth. And all of these features are really connected to the fact that the self-energy is non-Hermitian and frequency dependent. Okay, so far so good. We are we know that the mathematical object we would like to use to describe experiments like the photoemission case, but I mean any experiment really dealing with the excitations of n+1 and n-1 systems can be cast into the Green's function. So now we want to have a practical way to compute the interacting Green's function. Probably the most popular one so far, at least in this community, is the so-called GW self-energy. This comes from early work by Lars Sedin, and that basically rephrased the problem of interacting electrons in an exact way, introducing or making explicit quantities like the screen Coulomb interaction. So while standard perturbation theory builds just on top of the bare Coulomb interaction, there are advantages that can be foreseen if instead of the bare we use this screened one, since this is weaker and it's easier to treat in perturbation theory. And basically this screened Coulomb interaction can be seen, okay, it obeys a Dyson equation, then can formally be seen as the solution of a geometric series, but this is just math. But all of this boils down to some very complicated and unknown quantity that is this vertex object here, down here. So once, if we knew the vertex, basically we could compute the polarizability from and the self-energy, and then basically we would have solved the problem. So this is the complicated object. It's not really formal, but pretty much as the exchange and correlation functional or action is for DFT or TD-DFT. And here, so is where we want to make approximations, and in order to arrive at the GW approximation, it's simply, we can simply drop this term, so consider the vertex as a point, and then these deltas propagate to the polarizability function here and to the self-energy. So if we do this, basically, so we take a point vertex, the polarizability gets the direct product of two Green's functions, so it can be seen as independent particle or RPA polarizability according to the jargon, and the self-energy becomes the direct product of G and W, so from which the name of the approximation. So this is quite well known. I don't really want to use diagrams extensively, but just to use them to somehow graphically display equations. So in this language, the GW self-energy can be seen as the G, is the line, times the thick wiggly line that is W, and this can be expanded into this with the bare interaction that is nothing else than R3-Fock, I'll show in a second, plus this interaction expanded with bubbles that creates the RPA screening for W. So important thing, one of the important messages to take home here is that GW is not the whole story. So we have dropped a bit of the, we have made approximations in the equations. In other language, in other terms, we have dropped diagrams in our expansion. So GW is not the end of the story, and there are some diagrams that are missing already at the second order. And this I'm going to discuss in a second. So this has implications about the physics we can hope to get out of GW. Then again, for formal analogies, if we have no screening, so we substitute the screened Coulomb interaction with the bare Coulomb interaction, we have an approximation that is GV, and this is nothing else than the usual, well-known textbook R3-FOC approximation. So somehow GW can be seen and thought as a screened version of a properly dynamically screened version of the R3-FOC self-energy. And also, more interestingly, I think, some known approximations in chemistry, like the MP2 total energies, can be connected to to the so-called second-born approximation for the self-energy. Again, what we have to bear in mind is we have total energies and we have potentials that we can derive from total energies. So MP2 is the total energy, the second-born approximation is basically the related self-energy. And if we look at this, second-born basically has just the first-order exchange, the first second-order bubble. So this is the first second order because we have two interaction lines direct term, and then it has a second order exchange term. If we, but then it stops here. If we look at GW, we have again exchange and then the second order direct bubble, and then we keep on increasing the number of bubbles up to infinite order, and this infinite order sum is dealt with exactly. So it's summed exactly with the geometric series. But we are already missing this second order diagram here. So somehow already at second order in GW we have a direct term that is this bubble screening that is not matched by its exchange bit. And I think this is already a way to see how GW won't be exact for one electron system. So GW would bear some self-interaction, in this case some self-screening, exactly because at the second order these diagrams are not matched. In R3-FOC we don't have this problem because direct and exchange terms are matched. Here they are not. And I think this can already be seen from here. And this has consequences, of course. I'll come back to this in a second. Nevertheless, so if we look at solids, these are band gaps of solids. Red is LDA and light blue is GW. We see that when compared to experiment, we correct pretty much the fake Cone-Sham LDA band gap towards more meaningful and physical results. Similar things happen for molecules. This is the negative of the HOMO value interpreted as the ionization potential. The level of the GW theory used in these two practical applications is different, and this is going to become clear by the end of the talk. So unfortunately, and this is at variance with the density functional theory, which I think can be considered now to be consolidated. There are many implementations, but they can be validated against each other. There are still several different recipes to implement GW approximation, to make slightly different approximations to the GW results, and the situation is quite complicated. So one needs to be very careful when comparing GW results obtained by different groups, different methods, different implementations. Okay, so far so good, but as I said, GW bears self-interaction, and this has been, that is actually self-screening, this has been connected to the RPA polarizability. This is well known in the quantum chemistry community, for instance. They know very well that RPA is not self-interaction free. And GW is not the whole story. There are missing diagrams, and usually all the missing part undergoes the name of vertex corrections, and from time to time these are relevant. Depends on the system you want to treat, strongly correlated, or if you want to look at some very specific features of your photoemission spectrum, like satellites and so on. It could well be that GW is not enough. Oops. And also, GW is not, so we can further complement GW with some other missing diagrams to improve on the description of the spectral density, but also when looking at a direct comparison with ARPES, we can model something that is not included in the first step of the three-step model. So we can include also extrinsic losses, and this is done here in a model way, but it's very instructive. So somehow here we have GW results as compared, this is ARPES up to a quite large binding energy, this is GW, and then we have GW with corrected with cumulant expansion with intrinsics only, that is the green, or also including extrinsic losses. Okay, so this is more or less what we can get or what we can hope to get out of a GW calculation, what we cannot hope to get, and so on. Now let's look at how this is implemented in practice. So far we have seen equations and diagrams. So from we are still halfway to the actual use of this equation. Okay. So we had this expression here, where basically we have an eigen problem with a orbital dependent or frequency dependent non-local operator. This operator can be seen as the direct product of these two quantities, and where the direct product is also both space and time. If we go to frequency, to the frequency domain where we are more comfortable, usually this being a direct product in time becomes a convolution in frequency, and W is then related to the polarizability, and the polarizability again is a direct product in time and space and a convolution in frequency. So you can already see here that there are a lot of options. I want to use a real space basis, real time, or there are proposals to go to imaginary time, or I want to work with frequency space, or I want to use a plane wave representation that is more compact, or even go to a localized basis set. There are infinitely many options, and the math you have to undergo or to take here is quite complicated, and more than that is a lot of calculation. So it's not that you can simply take it and implement it right away, otherwise it is going to take forever. So one needs to be smart, and there have been a lot of proposals. Just to the very early ones are just reciprocal space frequency domain. That is also what I'm going to discuss here, and then some smarter in terms of algorithmic implementation, real space, real time. One can use the mixed representation, exploiting at best real and reciprocal space. Use of localized basis set, pretty much alike what happens in quantum chemistry, or localized Van function, up to also avoiding some sums over empty states that by the very end of the day turned out to be one of the killing tasks to be accomplished to compute a GW self-energy. Okay, so here we'll just focus on the very, let's say, simplest or most popular flavor of GW that would that is called in the jargon the G0 W0 approximation plus in the plasmon pole approximation. This is pretty much what was done in this paper here. So G0 W0 means that the Green's function is built on top of the Kohn-Sham DFT electronic structure. So basically this G0 is just the Kohn-Sham DFT Green's function that I can, for instance, represent as a sum over states using eigenpairs from the Kohn-Sham DFT. Okay. I think this is not strictly required by this naming, but in the community also G0 W0 means that wave functions, that quasi-particle wave functions are assumed to be equal to the Kohn-Sham DFT1s, that somehow representing the self-energy, or the Green's function, sorry, on the basis of the Kohn-Sham DFT electronic structure means that we are dropping off diagonal elements on this basis of the self-energy. I put this in brackets since it's not really strictly related to this naming, but is usually assumed in the community. And then last but not least at all is that in order to compute the self-energy, there are integrals over frequency that are very complicated or could be very complicated, and the plasmon pole approximation is just a way to approximate the dynamical behavior of W and get those integrals analytical. I'll very shortly review this, what this means in practice. So this is our self-energy, G naught, W naught. We want to, G naught is just the Green's function at the Kohn-Sham DFT level, as I said, can be represented as a sum over states here, and the polarizability also can be represented as a sum over transitions, where this C and V stand for conduction and valence states. We are left with this integral over frequency, and this is done or can be addressed in the plasmon pole approximation. Somehow here I'm looking at epsilon minus 1 that is just proportional to W. This can be represented in a spectral Lehmann, oops, this doesn't work, in a Lehmann way like the first line. The plasmon pole approximation basically consists, once we are on the QGG prime basis, on a reciprocal lattice basis, to take each component of this matrix to be just to have just a single pole. So just one pole to describe each single component. As I said, this allows for an analytical treatment of the integrals, so simplifies enormously the computation, can be motivated on a physical ground. So if we look, for instance, at the loss function, so the electric function of the system, we can spot or identify a main peak that governs the screening. There are several recipes so far in the literature about how to compute these residuals here in these pole functions here. I think the two most common are the Iberts and Louis that came first, and then the God-Benitez plasmon pole. In the Yambo implementation, we're going to use the God-Benitez one. This works most of the time, but not always, and I think there is more and more concern or understanding in the community that we need to be very careful about this. And just to mention one of the work where this was clearly pointed out is this work by Andrea Marini on copper, or we can look at recent works on zinc oxide. So there's plenty of literature about failures of plasmon poles. Still, this is kind of the working horse of is the simplest implementation of GW we can have. Finally, if we take the quasi-particle wave function or the Dyson orbitals to be equal to the Kohn-Sham orbitals, basically we can resolve the Dyson equation and compute the quasi-particle energies in first-order perturbation theory, meaning that we take the perturbation here, so we take out Vxc and we add the self-energy and consider this as a perturbation, and then we take the expectation value, and it's here. And again, we do the same trick of we linearize the frequency dependency of the self-energy, and we end up with an expression that basically has the expectation value of the perturbation weighted by the renormalization factor to be added on top of the Kohn-Sham eigenvalue, and the renormalization factor again comes or is related to the frequency dependency of the self-energy. This is pretty standard technology. It's not the only option. It's just probably the most common. Okay, here is a summary of a very simple G0 W0 flow chart. We start from a quantum engine, so the eigen solution of a DFT Kohn-Sham problem in terms of eigenvalues and wave functions. With these two quantities, we can separately compute the polarization, the polarizability, the independent particle polarizability, and the independent particle Green's function. And then if we put these two things together with knowledge of the plasmon pole approximation, we can compute the G0 W0 self-energy and eventually the quasi-particle corrections. So how it works in the very, very, very everyday practice. So first of all, that when it comes to real life, life is more complicated than on the screen. So here is an expression for the matrix element of the exchange self-energy or the correlation self-energy done on an implementation that takes into account the fact that we are dealing with a periodic system. So we have K and Q vectors summed over the Brillouin zone in a reciprocal space implementation. And so what we see here is that we have integrations over the Brillouin zone. These sums over Q basically are the so-called sums over transfer momenta. So Q in the Yambo jargon, but I think also in the more or less in the community jargon, while K usually labels electronic states, Q are differences of K, so they are transfer momenta, and we need to sum and check that those sums over the Brillouin zones are converged. There are sums over empty states. Those are quite annoying. Those come from the spectral representation of the Green's function. There is a frequency integral that usually lead to the plasmon pole, to the use of the plasmon pole approximation, and there are wave function and operator representation. So here we are using a reciprocal space basis, GG prime. Other options are possible, but these representation need to be considered and checked. So here is a snapshot of the Yambo input file, and all these quantities actually correspond then to input parameter you have to provide or you can control within the input file. So integration over Brillouin zone would correspond to the fact that you have a number of K points and Q points, and you may want to check convergence. So to rerun your calculation with different enlarging your sampling, and you have plane wave cutoffs here and there. You need to converge the calculation of the screening in terms of transitions that you put into the sums, or in terms of the GG prime, so basis representation of your screening operator. Plasmon pole approximation, we should probably check its validity or its how reasonable this is, or how our results depend on the position of the plasma, of the energy we use to perform this fit. We have, again, other sums over empty states, and I think this is the main message I want to convey here, is that at variance with the regular, let's call them regular, DFT calculations, I think that GW calculations are pretty much time consuming, but the problem is not the time of a single calculation. The problem is that in order to have a fully converged result, you may need tens, if not more, of calculations. And care must really be taken, since these parameters are not all independent. They can be mutually pair dependent. So convergences can be quite complicated, and I think care really need to be taken here. Here I just left some references. I think the slides are going to be available, so just to mention that some references can be found here, and I should be done. Thank you. Yeah. So since